Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and this is part one of a series of videos on logarithms. This video is an introduction to logarithms, and I want to start with something that you're familiar with. When we have an exponential relationship, I'm going to call my base b. I'm going to call the exponent x, and I'm going to call my quantity q. We can express this same relationship between these three variables in log notation. And the way that we do that is we isolate the exponent, x, and that will be equal to the log of q base b. We don't say the log of b, even though b follows, it's actually a subscript. That just tells us the base. So it's the log of q base b. So the log of a quantity is the exponent to which a certain base must be raised to equal the quantity. Let me write that out in words. So the logarithm of a quantity is the exponent to which a particular base must be raised in order to equal the quantity. So a logarithm is an exponent. And if you can think of it in terms of your exponential notation, it helps give you that understanding. Let's take a look at an example. We know that 4 cubed is equal to 64. Therefore, we could say 3 will be equal to the log of 64 base 4. So 3 is the exponent in that relationship. 3 is the log of 64 base 4. I think it will be helpful if we take a look at taking things in exponential form and rewriting them in log notation, and then taking relationships in log notation and expressing them in exponential notation. So let's do that next. So I have 4 examples here of exponential notation. We're going to write the same relationship, but we're going to write it in log notation. And I've just written here, remember b to the x equals q, that's our exponential notation. And the way we can rewrite this is x will equal the log of q base b. So in our first example, we would say the exponent, which is 2, will be equal to the log of the quantity 25 base 5. That's all. Second example, same thing. We would say the exponent, which is 4, will be equal to the log of the quantity, which is 16 base 2. We will encounter negative exponents in logs. So in this case, our exponent is negative 2. It will be equal to the log of the quantity 1/9 base 3. So 3 to the negative 2 equals 1/9 can also be written as the log of 1/9 base 3 is equal to negative 2. 9 to the 1/2 equals 3 could also be written as the exponent, which is 1/2, will be equal to the log of the quantity 3 base 9. So it's very easy to get confused with these, unless you can think of them in exponential notation. Then I think it makes it a little bit easier. Now let's do some examples where we have log notation and we want to express in exponential notation. So let's take these examples and express them in exponential notation. We start with our base. Our base in our first example, we know that 3 equals the log of 1000 base 10. So 10 is the base, the exponent is 3, and the quantity is 1000. So it's this expression, this relationship is saying that 10 cubed is equal to 1000. Same thing with this one, I just flip sides, doesn't matter. We start with the base 2, the exponent will be 5, equals the quantity 32. So 2 to the 5th power is equal to 32. Similarly, negative 1 equals the log of 1/4 base 4. So we start with our base of 4. raise it to our exponent of -1, equals our quantity of 1/4. So 4 to the -1 equals 1/4. And 2/3 is equal to the log of 4 base 8. We start with our base, 8. Here's our exponent, 2/3 equals 4. So 8 to the 2/3 is equal to 4. We learned in the video on exponents that that's true. Get comfortable with going back and forth from one notation to the other. It's extremely important when you're working with logarithms. Once you've done some examples like these, then take a look at the next thing that you'll probably be asked to do, and that is solve for an unknown in these relationships, in these logarithmic relationships. So let's take a look at some examples of that. Okay, in these questions, what we're going to do is solve for the unknown. So find the value of, in this first example, q. That's going to be the easiest type of question you encounter with these log questions, because all you need to do is express this in exponential form, and then q will be isolated. So we know that the base is 4, the exponent is 3. So 4 cubed equals q. So 4 cubed is 64. So q is equal to 64. Second example, very similar. We have our quantity unknown, so we take our base of 5, our exponent of -2, and we find q. So 5 to the -2 is 1 over 5 squared. We learned that in the video on exponents, the laws of exponents. And we can leave it like that, or we can express it as 1 over 25. So it's fairly easy to find q. Just go to exponential notation and q will be isolated, and then you just evaluate. Gets a little trickier if it's the base that's unknown. So let's take a look at that. Okay, in these next examples, we're going to solve for b. Again, we're going to go from log notation to exponential notation. So b to the exponent of 2 is equal to 100. So I know that b squared is equal to 100, and if you can tell the answer immediately, that's fine, but it won't always be quite as easy. So what we're going to do is raise this to a power so that the product of the two powers is equal to 1. So you raise it to the reciprocal. So the reciprocal of 2 is 1/2. What you do to one side of the equation, you do to the other. In this case, what I'm doing is I'm taking the square root. But I'm showing you this method because sometimes your exponents are not going to be that easy, so we want a strategy. So b squared to the 1/2, we multiply those two exponents. So we get b to the 1, 1/2, 100 to the power of 1/2 is the square root of 100, which is 10. So b equals 10 is our solution. Similarly with this question, we're going to put it in exponential notation. So b is the base, the exponent is 3, and equals 8. I don't want what b cubed equals, I want b. So I'm going to take the cubed root, or in other words, I'm going to raise this side of the equation to the power of 1/3, and I have to do the same thing to the other side. Again, you need to know your laws of exponents, and if you don't, go back and review them in those videos. Now I know that b cubed to the 1/3 is b to the 1. We multiply those exponents, and the cubed root of 8 is 2. Okay, our next example, again, we're going to go to exponential notation. So b is the base to the power of -2 equals the quantity of 1/16. So what I'm going to do here is I'm going to raise this to the power of -1/2. So you raise it to the power of this reciprocal of this exponent, so that when you multiply those two things, you get an exponent of 1. We do the same thing to the other side. So we're going to get b to the 1 power will equal First of all, I'm going to deal with the negative exponent. So when we have a negative exponent, we take the reciprocal of our base. So that becomes 16 to the 1/2, which is like the square root of 16. So our base must be 4. And we can check it. Does 4 to the negative 2 equal 1/16? Yes, it does. So we know it's correct. Do the same thing here. We have b to the exponent of 1/5 is equal to 2. I just wanted to know what b is equal to. So I'm going to raise this to the power of the reciprocal of 1/5 is 5. I do the same thing to the other side. So 1/5 times 5 is 1, so I'll get b to the 1, which is just b. 2 to the 5th power is 32. Does 32 to the 1/5 equal 2? Yes, it does. So that's how you would solve for b if that's the unknown. Let's take a look at some examples where the exponent is the unknown. So if we have an example where x is unknown, the exponent is unknown, we're still going to go to exponential notation to help us solve this, because we do not have functions on our calculator that we do have log functions, but they're only good with certain bases, which I'll talk about in a couple of videos. So right now, I can't find the log of 8 base 2. We do not have a function on our calculator that does that. Most calculators don't have that function. So what we're going to do is rewrite this in exponential notation. So 2 to the x will equal 8. Now when you're finding the exponent, what you want to do with your quantity is you want to try to think of that quantity as a power with 2 as a base in this case. So we know that 8 can be written as 2 cubed. So if 2 to the x is equal to 2 to the power of 3, the only way that can happen is if the exponents are equal. Once the bases are equal and the powers are equal, then therefore the exponents must be equal. And we can do a check. Does 2 cubed equal 8? Yes, it does. Our next example, we do have a log base 10 on our calculators, but I don't want you to do it that way at this point. I want us to rethink it in exponential notation. So my base is 10, the exponent is x is equal to 0.1. We have to see if we can think of 0.1 as a power of 10. Well, we know that 10 to the negative 1 is equal to 0.1. So we want to express it that way. Once we have our two powers written in the terms of the same base, then we know our exponents must be equal. So x must be equal to negative 1. Let's try one or two more. In our next example, we have x equals the log of 8 base 4, so we rewrite that. 4 to the power of x is equal to 8. We look at our quantity and see if we can write it in terms of this base, and we can't. We can't write 8 as 4 to the power of something. However, both 8 and 4 can be written as powers of 2. So we're going to do that. So we're going to write 4 as 2 squared. And we're going to write 8 as 2 cubed. Laws of exponents say that this will be equal to 2 to the 2x is equal to 2 cubed. Now we have the two powers are equivalent and our base is the same. Therefore, the exponents must be equal. So therefore, 2x is equal to 3 and x is equal to 3 halves. We can plug it in. Does 4 to the 3 halves equal 8? And it does. So you will be asked to solve for different unknowns in this relationship, and you now have a strategy for doing that. So practice that, and when you're comfortable working from exponential to log, log to exponential notation, you're comfortable finding these unknowns, we're going to proceed to the properties of logarithms in the next video.